Yeah. Guys. So what were we discussing yesterday?
So the last topic we discussed was Gauss law and magnetism.
Yeah, Gauss law and magnetism. That was okay. Listen. So the next topic that we are going to discuss is the terms related to the magnetic properties of a material. Okay. So yesterday I told you one point, right, that every material will have magnetism, but the extent to which the magnetism of a material is dependent on is decided by certain parameters. Okay. So let's see what they are. We are going to describe certain magnetic properties of a material which are required for us to understand. First, the first word that we are going to see is called as the magnetic permeability. Okay. Here the order is slightly swapped. Anyways, I will explain with this. See, first term that you need to know is, please write it down. Here the term is missing. The first term that we need to know is called as the magnetic induction. So the name itself is suggesting something. What do you mean by magnetic induction? So before that, let me switch on my video. Let me explain you certain facts of why we are studying this topic. See, I just want to ask you a few questions, guys. I don't have a magnet in my hand, but if possible, I'll try to show it tomorrow. Now, if I have a magnet with me, and I take that magnet and connect it across a particular material. Okay. I'm not sure if you guys have ever observed it. You take that magnet and take it close. See, suppose you take a magnet close to an iron particle or an iron substance. What do you think will happen? If the magnet is directly taken, it will attract. Okay. Suppose this is the iron substance. I'm holding this object with the help of a magnet. Okay. And I'm taking this iron substance close to another iron substance. What do you think this iron substance will do to the other?
It'll attract.
Means this iron substance will have some magnetism inside it, which will help attract the other magnetic property, other magnetic materials. Means this iron substance need not be as strong as the original magnet. But what would have happened is, the original magnet is there, right? That magnet would have induced certain field in this magnetic material, due to which you take it close to another magnetic material, it starts attracting it. Are you guys able to understand this point?
Yes.
Okay. So the external magnet is what is called as the field produced by the external magnet is called as the magnetizing field. That I'll explain the next point as. Okay. So that magnetizing field plus the field generated within this material is what is called as magnetic induction. Okay. So that is the first topic that we are going to see. Guys, I'm repeating again with a diagram. Try to understand. Okay. If there is any doubt, get it clarified. Suppose I have an external magnet which has a north pole and a south pole. So this external magnet will have a region of magnetic field around it. Right? It will have a region of magnetic field around it. Accepted? Guys, 1 minute. No? 1 minute. I think I have that sheet. Yes, I do have it. Listen. So inside a material, right? Inside, so when you take it close to a magnetic substance, I hope you're able to understand what is the difference between a magnet and a magnetic substance. Right? Magnetic substance is a material which can exhibit the property of magnetism. Means it need not be a magnet, but if it is placed in the presence of an external magnetic field, it will start exhibiting magnetism. That is what is called as a magnetic substance. Now, what we are learning is everything related to a magnetic substance, not to a magnet itself. Try to understand. So, can I say something like this, guys? Every magnetic substance is made up of atoms. And since it is made up of atoms, the electrons are going to be in continuous revolution. Due to the electrons being in continuous revolution, can I say that there will be small dipoles that will be present, which have a dipole moment associated with them? Can I say it like this?
Yes.
Right. So let's say, let me put it with an arrow mark. Let's say there are small dipoles existing in that material in such a way that the net dipole moment of that material, of the substance, before you place it in the external magnetic field, is going to be zero. This, see, look at this dipole moment. This dipole moment is in some random direction. The second one is in some random direction. So everything will get added and they will get cancelled out. They'll get vectorially added and they will get cancelled out such that the net magnetic dipole moment of this material is going to be zero. Correct? Now, if I take the substance and put it in an external magnetic field, if I put it in an external magnetic field, what do you think will happen to these dipoles? Before that, I have a question. If I have drawn the external magnetic field like this, then which is north and which is south? Which is north and which is south, guys? So magnetic field is always from north pole to the south. Right. So what will happen to this dipole? And we know that the dipole moment is from south to north. Right. Can I say that these dipoles will start experiencing torque and they will get aligned in the direction of magnetic field in this scenario? Guys,
Yes.
does it? It is something like something similar to a dielectric placed in an external electric field. Right. So instead of a dielectric, what are we doing in this context? In this context, we are taking a magnetic substance and placing it in the presence of an external magnetic field. So when we do this, the dipoles will get arranged in such a way that there will be a net dipole moment which is not equal to zero. Correct? So as a result of which, can I say that there is going to be some magnetism present inside this material also? Right. That induced magnetic field is what is given by the formula. It is given as the sum of magnetizing field. Please write it down. There are 5 terms. Sorry, I think there are 7 terms. They will confuse you. Okay, please write it down. Magnetizing, magnetization, all these terms will confuse you. So ensure you write it. So now what am I trying to talk about? I'm talking about magnetic induction. So magnetic induction is defined as the sum of whom magnetizing field plus the induced field. I'll write it as magnetic induction. So magnetic induction in this chapter is represented by the symbol capital B. Guys, did you understand what I meant? Is everyone clear with this?
Yes, sir. Yes.
Yes, sir.
Good. So sum of magnetizing field plus induced field is what we call it as magnetic induction. Now I have a question. So now you understood what is meant by induced field. Where is it getting generated from? It is getting generated when the dipoles inside the magnetic substance experience torque and they get aligned in the direction of magnetic field. Right. Now, what do you mean by magnetizing field?
Sir, any field that magnetizes or aligns the dipoles.
Very good. Very good. So we need some external magnetic field to make these dipoles get aligned in the direction, right? That external magnetic field, which is giving the magnetic property to a substance, is what is called as magnetizing field. Okay. So I'm going to show you the definition of it. So in this material, it's given in the reverse. So first is magnetizing field. So I'll read it out. Listen to this. Okay. When a magnetic material is placed in a magnetic field, a magnetism is induced in it. This is a known fact, right? So the magnetic field that is able to induce the magnetism is what is called as magnetizing field. For example, if I take a solenoid, okay, last chapter we discussed about a solenoid. The solenoid is wound around a material called as soft iron core. Now tell me guys, when you start passing the current through the solenoid, right, what is getting generated within the coil? That we have already seen. There is a magnetic field that is getting induced of value B is equal to mu naught into Ni, where mu naught is the permeability of free space, small n is the number of turns per unit length, and I stands for the value of the current. So B is equal to mu naught into Ni, and this field will have the tendency to magnetize the soft iron core. Accepted. So that B is equal to mu naught into N into I is one of the examples of a magnetizing field. It's not necessary that you need to always use a solenoid. You can use a permanent magnet also. So whichever material is inducing magnetism in other material is what is called as magnetizing field. So with the hope that this definition is clear, I'm moving on to the next one. Shall I move on?
Yes, sir.
Right. The next topic that I already told you is magnetic induction. So what is magnetic induction? Magnetic induction is nothing but the sum of the
Magnetizing
Sum of
field and
magnetizing field plus
field
induced field.
plus the field that is induced inside. That is what we call it as magnetic induction. So that's what is given here. See, the total magnetic field inside a magnetic material is the sum of the external magnetizing field and the additional magnetic field produced due to magnetization of the material. That is what we call it as magnetic induction. Okay. That is, see, always there will be alternate definitions also. Okay. That is in terms of a permanent magnetism. Sometimes you can speak in terms of current also. So the magnetic induction can also be defined like this. It can also be defined as the total number of magnetic lines of force crossing unit area through a material. Please write it down. Alternate definition for magnetic induction is, it can also be defined as the total number of magnetic lines of force crossing per unit area normally through the surface. To put it in simple terms, the number of field lines are generally what are called is called as flux. Like how you learned electric flux, you will be learning about magnetic flux in the next chapter. The amount of magnetic flux per unit area is also called as magnetic induction. That is what they are trying to say. Okay. That is why if you see the SI unit of magnetic induction, it is nothing but magnetic field is basically. Just a different name is given. That's it. Its unit is Tesla, or it is written as Weber per meter square, where Weber is the unit used for magnetic flux. You will learn it in the next chapter. Weber per meter square, which is also equal to this value, Newton per meter per ampere, or Joule per ampere per meter square. Okay. Next, the third definition is magnetizing field intensity, which is represented by the symbol H. This term magnetizing field we have already learned. Now again, why are we learning something called as magnetizing field intensity? What do you think is the difference? You can guess from the name itself.
So the intensity of the magnetizing field.
Yes. So intensity means the strength of it. Right? See, I'll give you an example. Suppose I'll take the same solenoid. Let's say I'm giving you two solenoids, guys. Okay. And in both the solenoids, let's say you're passing the same amount of current. But in one of the solenoids, the number of turns per unit length is 5. And in the other solenoid, the number of turns per unit length is 10. Okay. Which one will technically have more magnetizing field intensity?
The second one.
Why?
So it has a more number of turns, thereby it increases the intensity, the strength of the magnetic field or the magnetizing field.
Yes. You're able to understand. So the ability, so which one can magnetize another material easily is an important question that we need to ask. So I give you a small bar magnet and a bigger bar magnet, whichever is able to induce magnetism in the magnetic substance fastly, that material is said to have greater magnetizing field intensity. That is why the definition starts like this. The ability of a magnetizing field, the ability of magnetizing field to magnetize a material medium is expressed by the symbol H, and it is a vector quantity. And this H is what is called as magnetizing field intensity, or in simple terms, we just call it as magnetic intensity. They both mean the same. Okay. So as I told you, there will be one basic definition and there will be some mathematical definition. So here the mathematical definition is like this. Its magnitude may be defined as the number of ampere turns flowing around the unit length of the solenoid required to produce the given magnetizing field. That is, if you say B is equal to mu naught into N into I, this is a magnetizing field of whom? Of a solenoid. Okay. If you take this term N into I, then this N into I is what is technically called as the magnetizing field intensity of a solenoid also. So from that example, they have given a definition to magnetizing field intensity. What is the mathematical definition of it? It is the number of ampere turns, that is capital N into I per unit length. Okay, but capital N by L can be written as small n. So small n into I. So H can also, the magnetizing field intensity can also be written as small n multiplied with I. Am I clear, guys? So what can you conclude is B naught is equal to mu naught into Ni for a magnetizing for a solenoid. So this N into I, you can write it as capital H. That is what they're trying to say. Or capital H can be written as B naught divided by mu naught. Now you guys tell me what is going to be the SI unit for it. It is the number of ampere turns per unit length. Number doesn't have a unit. I is measured in ampere, L is measured in meter. So ampere per meter is what is that? Is the unit of magnetic intensity. Okay. Moving on to the next concept. The next one is called as intensity of magnetization. So previous one was magnetizing field intensity. Now we are saying intensity of magnetization. What do they mean by that? Are they both same or different? What do you think is going to be the answer? Here, we need to take this concept into consideration. In the first point, I told you, right, that the dipoles will get aligned in such a way that they experience the maximum. They will get aligned in such a way that it is in the direction of the magnetizing field, right? So they have some amount of dipole moment associated with it. So let's say the dipole moment of this material is mu1, of this is mu2, mu3, mu4. Then what I can do is you can add them vectorially. What do I mean by vectorially? Means that you can add them along with the direction. So if you take a unit volume of that material, see, basically this will be the shape of a cuboid. From that cuboid, what I'm taking is I'm taking a unit volume, and in that unit volume, if you are able to calculate the total magnetic dipole moment, okay, you calculate the total magnetic dipole moment and divide it with the volume that you have considered, then that parameter is technically called as intensity of magnetization, or in very simple terms, you just call it as magnetization. That's it. Okay, this is a definition. The magnetic dipole moment developed per unit volume of a material when placed in a magnetic field is called as intensity of magnetization, or simply magnetization. I hope there is no confusion, right? I hope it's clear, guys. Yes?
Yes, sir.
Yes, sir.
Yes, sir.
Good. Now, we need to see another mathematical definition for it. I'll come to that later. Okay. As of now, have this point in your mind. That intensity of magnetization is the total magnetic dipole moment developed per unit volume. Then we have something called as magnetic permeability. So what is magnetic? So till now we were discussing about what is magnetic permeability, right? Now we are going to give a definition to it. So permeability, as the name suggests, is a measure of the extent to which a material can be penetrated or permeated by a magnetic field. Means how much allowance the material is giving for magnetic field to get generated within itself is what we call it as magnetic permeability. So the magnetic permeability may all, that is the basic definition, and the mathematical definition is like this. Magnetic permeability of a material can also be defined as the ratio of its magnetic induction to the magnetic intensity. I told you already, B is equal to, you guys remember this? B is equal to mu naught, B naught is equal to mu naught into H naught, right? So can I write B is equal to mu into H, where mu is the permeability of a given material. It's not permeability of free space. Mu is the permeability of every material. Till now we were using mu naught by 4 pi everywhere. No. Here mu naught represents what? Mu naught is the permeability of free space, whereas mu is the permeability of a material. So how can you write mu as? It is defined as the ratio of the magnetic induction to the magnetic intensity in the material. So what will be the SI unit of mu? Let's see. B is measured in Tesla. H is measured in ampere per meter. That is why if you see mu naught by 4 pi is equal to 10 power minus 7 Tesla meter per ampere. The unit comes from here also. Clear, guys? This is magnetic permeability. Now there is another concept which is called as relative permeability. What is it? So there is something called as relative permeability. So I
So
would
the
have already
comparison between two magnetic permeability.
very the comparison between two magnetic permeability. That's right. See, for example, I ask you what is relative density data. So what is relative density? It is the density of substance,
Density of water.
density of water at 4 degrees Celsius. So generally, whenever you see relative, you do a comparative study between the physical quantities of same nature, right? Relative refractive index of a material to the refractive index, refractive index of a material to the refractive index of vacuum or air, whatever you can say. You can say something like this, right? So you will say something like the speed of light in a given material to the speed of light in vacuum. In a similar way, relative permeability is something like this. It is the permeability of a material. It is a ratio of the permeability of material to the permeability of free space. If I have to be more specific in the case of electrostatics, there is something similar to relative. Do you guys remember there is something called as relative permittivity?
Kappa.
Yeah, relative permittivity. What is the other name for it? The one which starts with D. It is also called as dielectric constant. Relative
Yes, sir.
permittivity is also
Kappa.
called as, yeah, kappa is right. Relative permittivity is also called as dielectric constant. In a similar way, there is something called as relative permeability in magnetism. But it doesn't have any other name like dielectric constant or something. You just call it as relative permeability. That's it. Okay. So if you take, for vacuum, if you calculate the relative permeability, it is 1. For air, it is 1.0000 something 4. For iron, the value of relative permeability is greater than 1000 because it's a ferromagnetic substance that we will see later. Clear, guys? I hope there is no confusion, right? Next is magnetic susceptibility. Okay, magnetic susceptibility, which is also written as, you know the symbol, right? It's called as chi. It's a Greek letter. So magnetic susceptibility means vulnerability. So what do you mean by vulnerable?
So weakness.
Yes. More than saying it's a weakness, the extent to which something can be affected. Right. Or I can be more like this, the extent to which something can be influenced. So here, magnetic susceptibility is what we are trying to define for a magnetic material, right? So how do we define it? Magnetic susceptibility is another parameter. These are all the measuring quantities. These are all the quantities which help us to understand the extent to which a material can be magnetized. Okay. So magnetic substance susceptibility measures the ability of a substance to take up magnetization when placed in magnetic field. Okay. So that is a basic definition. And the mathematical definition is like this. It is defined as the ratio of magnetization to the magnetic field intensity. To put it in very simple terms, you guys know what is efficiency. Efficiency is basically output by input. Correct? That is a known fact. Efficiency basically means output divided by input. Now, with respect to a magnetic substance, what is the output expected from it? It is the extent to which the material is magnetized. What is the input given to it for it to get magnetized? It is the magnetic field intensity. Correct? So chi-m, if you talk about susceptibility, basically it means the extent to which a material is getting magnetized when you give an input value of H. That is why it is defined as the ratio of magnetization to the magnetic field intensity. And if you observe an important point here, magnetization and the magnetic field intensity, they are dimensionally the same. Hence, susceptibility is a dimensionless constant and it is just a number. So it doesn't have any units. Okay. The last point is relation between magnetic permeability and magnetic susceptibility. So relation between magnetic permeability and magnetic susceptibility. Shall I proceed? Now listen, guys. If there is a linear magnetic material, what do I mean by linear magnetic material is, what is the input that you give? The input that you give is H and the output you get is B. And what is the relation between those two? B is equal to mu into H. Right? If B and H are proportional to each other, okay? If B and H are proportional to each other, then you can say that particular material is a linear magnetic material. Okay. So if a linear magnetic material is subjected to the action of magnetizing field intensity and it develops an output of magnetization capital M, then can I say that the magnetic induction is nothing but mu naught into H? What is mu naught into H, guys? It is a magnetizing field plus mu naught into M. This is the induced magnetic field. Okay. So if I take the value of mu naught outside, it will be H divided by M. But what is B? B is also equal to mu H. This can also be written as mu naught into H plus M. So I'm going to divide with H on both the sides. Rather, I will divide with mu naught H on both the sides. Then what will happen is this mu naught and mu naught will get cancelled. This and this will go. So what is mu divided by mu naught? Mu divided by mu naught is nothing but relative permeability is equal to 1 plus what is capital M divided by H? That is magnetic susceptibility. So this is the relation. So the relative permeability is given as 1 plus the magnetic susceptibility. Please make a note of this. There's a very important one. Based on this, you will have one more questions that are being asked, that will be asked. Okay. So just go through these concepts. I'll be back in 2 minutes. Then we'll go to the next part of this chapter. Okay, please keep revising. I'll be back. So I hope you're done, right? Now listen, just a minute. I'll open a video and I'll show it to you. So the next topic is going to be about different types of substances. So listen, guys. I'm just showing a video.
Sir, are
Which
you
will help.
sharing the video?
I'm going to share it.
Okay.
Now see. So this is an experiment which is going to explain you about the different types of magnetism that is possible. One is paramagnetism, ferromagnetism, and diamagnetism. Okay. Now observe how the materials are going to respond. Based on that, we will have a further discussion.
You might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism.
See, this is what I
Ferro
explained at the
means
beginning.
iron.
Suppose you take an iron nail, that the long one, and you try to take close to pins, it is not getting attracted, right? But see what will happen if magnet is attached to the iron nail.
An unmagnetized piece of iron or nickel or cobalt becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field.
So did you guys understand what he
An important
showed?
example of a diamagnetic.
So the first thing that was shown was ferromagnetic. That iron nail was there. No, that is a ferromagnetic substance. Now we showed different substances. The copper sulfate, then aluminum. All those things were paramagnetic substances. Now he is going to explain how the diamagnetic substances are going to be. So, but before that, tell me what happened to a paramagnetic substance? Did it get attracted to magnetic field or repelled to magnetic field?
Attracted, sir.
Attract.
They got attracted, no? But see what will happen to diamagnetic
material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field
So this is called
present
as magnetic
when they're
levitation.
chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an
Did you
object is
understand this?
diamagnetic or paramagnetic is to see how it aligns
Yes,
itself
sir.
in a magnetic field.
Okay.
Yes, sir.
So based on that, we are going to discuss the concepts now. Okay. So basically, you have materials which are diamagnetic in nature, paramagnetic in nature, and ferromagnetic in nature. These are all the comparative studies we are going to do. Suppose somebody tells you the relative permeability of a material is between 0 to 1. Tell me what type of material can it be? Then it will be a diamagnetic material. Like we'll be taking different conditions and try to analyze the situation. Okay. Now listen. The first thing is effect of magnets. So what did a diamagnetic material do as soon as a magnet was brought close to it?
Got repelled.
So it repelled, but it was a feeble repulsion. Not like it jumped away directly. Right? It was a feeble repulsion. Whereas when you talk about a paramagnetic substance, it got attracted, but this was also feeble. Then what about a ferromagnetic substance? They got attracted, but they got attracted very strongly. Okay. Next is in external magnetic field, what will happen? Shall we see what is going to happen in the presence of external magnetic field? You see this example, and this example in the video itself.
Diamagnetic
So glass
objects
is a
like
diamagnetic
glass will
material and
rotate
it
to
has
avoid
magnet.
magnets.
See what is going to happen as soon as it brings the magnet, the glass between the magnets.
Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic
So
field.
what did it do? It got aligned itself along the direction of weaker magnetic field. But see what will happen to an
But
aluminum.
aluminum rotates into the field, typical of a parallel paramagnet. On the
So
periodic
it gets aligned in the direction of magnetic field. So based on this, can you guys tell me what kind of materials will exhibit paramagnetism and what material will exhibit diamagnetism?
Sir, metallic substances will represent paramagnetism, whereas non-metallic substances will represent diamagnetism.
How are you able to say that?
Sir, glass is a non-metallic substance, sir.
Okay, that is one of the examples that he has taken. But you in periodic table, you have a lot of elements, right?
I think
Yes, sir.
the number of unpaired electrons.
Yes. Yes.
So if it has some unpaired electrons, then it will be paramagnetic, and
Very good, very good. If it has an unpaired electron, it will be paramagnetic, whereas if it has everything as a paired electron, right, then it is going to be diamagnetic.
table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s
And,
and
1p,
1p.
right? So that 1p orbital
Now it's that
electron will be
unpaired electron
unpaired.
that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet, like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least one unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
I hope it is clear, guys.
Clear, sir.
So based on this, you can say now, what will happen when you take a diamagnetic substance and place it in external magnetic field? So it will generate, it will develop magnetization, which will be feeble, but in the opposite direction to the magnetizing field. Whereas a paramagnetic substance will acquire magnetization, which is feeble, but in the direction of magnetizing field. Okay. And ferromagnetic substance will also acquire magnetization, which is very much strong, and it will be in the direction of magnetizing field. Okay. Then what about in a non-uniform electric field? So when you place a diamagnetic substance in a non-uniform electric field, it started revolving, you remember? So when you place the glass in the direction of magnetic field, it started revolving and tried to acquire and started to align itself in the direction of weaker magnetic field. Okay. Whereas a paramagnetic substance will move from a move slowly from a weaker to a stronger part. What about a ferromagnetic substance? It tends to move quickly from weaker to stronger. So that is why if you observe paramagnetic and ferromagnetic, they'll be same, except the fact that paramagnetic are feeble, ferromagnetics are stronger. Right. Now, what can you say about susceptibility? So with respect to a diamagnetic substance, the susceptibility is negative because it is not vulnerable to get magnetized at all. It is not interested in getting magnetized. Whereas for a paramagnetic substance, the susceptibility is a small number. But for ferromagnetic substance, it is greater than 1000. It is that high. Now, what about relative permeability? So relative permeability for a diamagnetic substance is between 0 to 1. Whereas for a paramagnetic substance, it is greater than 1 and less than a small number. It will be somewhere closer to 1. Whereas for a ferromagnetic substance, it is greater than 1000. Okay. Similarly, if you talk about the permeability value of a diamagnetic substance, it is less than mu naught, it is greater than mu naught, and here it is very much greater than mu naught. Okay. The next is, what is going to be the effect of temperature on a diamagnetic substance? So if you see, the susceptibility of a diamagnetic substance is independent of temperature. Whether you raise the temperature or chill down, it is never going to get magnetized. So it has nothing to do with susceptibility. Whereas with respect to a paramagnetic substance, the susceptibility varies inversely with respect to temperature. That is, you keep increasing the temperature, the material will tend to lose its magnetic property. Whereas with respect to a ferromagnetic substance, susceptibility decreases with the temperature in a complex manner. It decreases as a function of T minus Tc, where T is the temperature and Tc is called as the Curie's temperature. Okay, so Curie's temperature is the temperature at which, I repeat, Curie's temperature is the temperature at which the material will get completely demagnetized. Means you start heating a ferromagnetic substance, there will be a particular temperature at which the material will lose its magnetic properties completely. That is called as the Curie's temperature. Okay. Next is, what will happen to a diamagnetic substance when you remove the external magnetic field? So diamagnetic materials will exhibit the magnetization, the negative magnetization, as long as the magnetizing field is applied. Same is the case with paramagnetic also. But with respect to a ferromagnetic substance, it will retain. Like you saw, no, that a big iron nail was there, that iron nail picked up certain pins and all those things. So it was able to hold some magnetism within itself. And that property is called as retention. We'll be learning about it later. Okay. Variation of M versus such. M stands for what? What does M stand for? M stands for magnetization. H stands for M stands for magnetization. H stands for magnetic intensity. So magnetization changes linearly with H. Whereas here, what will happen? Magnetization changes linearly with H, and it will attain a saturation at low temperature and in very strong fields. In the presence of very strong field, magnetization will attain a saturation. Whereas in the case of ferromagnetic substance, M and H will vary non-linearly. Okay. This hysteresis effect, I'll explain it tomorrow. Next is the physical state of the material for a diamagnetic can be solid, liquid, or gas. Here also it can be solid, liquid, or gas, whereas with respect to ferromagnetic substance, they are normally solids. Okay. And some examples are also given below. Clear, guys? So what does this hysteresis effect mean? That I will explain it in the next class. By next class, we'll be completing this chapter. Okay. That is by tomorrow, this chapter will be over. That's small. Because tomorrow I need to explain only hysteresis effect and Earth's magnetism. If not tomorrow, maximum will take one more class. That's it. Right. I hope you guys are clear with all the terms that we have discussed today and this table, right? Is
Yes.
there any confusion or a doubt?
No, sir.
Anyone?
No, sir.
No, sir.
That's good. Okay. So do one thing. We'll revise it. In tomorrow's class, we'll try to complete this chapter. Okay. So I'll see you all tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.